So, in the last lecture we had started our discussion of natural convection. Heated body in a colder ambient fluid, the temperature close to the body is higher and the temperature decreases as you go out into the ambient fluid. When the temperature is higher closer to the body, the density is lower, and therefore, in a gravitational field the fluid will rise along the surface of the body. And as the fluid rises, you can see that as the fluid rises, it takes away the heat along with it, and ambient fluid sweeps in to fill the space. Once again, that ambient fluid gets heated and then it rises and more ambient fluid sweeps in, and in this way you have a mechanism for heat transfer in addition to molecular diffusion. This is a convective mechanism for heat transfer, and this is called natural convection. The point here is that first of all there is a coupling between the momentum and the temperature field through the variation of density with temperature. Through the variation of density with temperature, there is a coupling between the momentum and the temperature field. So, basically the difference in density between the fluid at the surface of the object and the ambient fluid acts as a body force in the momentum equation, and this body force tends to drive fluid upwards. So, therefore, because of this body force, there is a continuous rise of fluid and sweeping in of ambient fluid to fill in the available space. This generates convection, and this mechanism can be much faster than diffusion or rather heat conduction in normal applications that we see. The velocity field for this is not determined from a characteristic velocity is not due to forced convection, due to the application of pressure or a force across the fluid. This is due to the body force that is automatically generated by the temperature variations. So, that is why it is called natural convection, and for this we have to solve the energy equation together with the mass and the momentum equations. We have to solve the energy equation together with the mass and momentum equations. Now, we had made several assumptions in what is called the Buoyancy approximation for the equations of motion. First of all, the density variation is a linear function of the temperature variation. So, the density varies linearly with temperature. Note that the density should actually decrease as the temperature increases as we have defined it, which means that the direction of acceleration due to the temperature variation goes from lower temperature to higher temperature or from higher density to lower density. So, this density variation is neglected, is linear, is a linear function of the temperature, where this beta is what is called the thermal expansion coefficient. Second, the density in the momentum, energy and the mass conservation equations, the density is replaced by a constant value, the density far from the object. In all the mass, momentum and energy conservation equations, the only exception being this gravitational force here. This gravitational force here alone we consider the variation in density. If we did not consider the variation in density here, there would be no forcing, and therefore you would generate no flow. So, therefore, we consider this only in this gravitational acceleration term. We neglect density variations in all other terms. So, the equations are like the equations for an incompressible fluid, except that there is a body force due to density variations. And similarly, we neglect viscosity variations. We assume that the viscosity is the ambient viscosity, and variations in the thermal conductivity. We assume that the thermal conductivity is the same as the ambient thermal conductivity. Okay. Okay. So, therefore, the equations that we got ultimately, mass conservation, divergence of velocity is equal to 0, momentum conservation, usual Navier-Stokes with the body force. Okay. I should note that in this particular case the acceleration is upwards. Okay. The acceleration is upwards because the acceleration is opposite in direction to the acceleration due to gravity, because when the density increases the temperature decreases. Okay. So, okay, or rather when the temperature increases the density decreases. Okay. So, you have this is basically a buoyancy force, and we assume thermal conductivity is a constant. We have done the scaling. Okay. Length is scaled by the characteristic length, which is the size of the object. Okay. The length is scaled by the size of the object. Okay. Velocity we do not yet know. Temperature T minus T infinity by T naught minus T infinity is our usual scaling. We scaled the gravitational acceleration by its magnitude, so that G star is just a unit vector, and the dynamical pressure scaled by rho infinity times V c square. I should note that in this equation we have defined the dynamical pressure as the difference between the local pressure and the hydrostatic pressure due to the density variations. Okay, the difference between the local and the hydrostatic pressure. Therefore, in the equation the forcing term is due to the difference in density between the fluid and the ambient density. Okay. So, that is the simplification we have done in the momentum equation, subtracted out the pressure gradient due to the hydrostatic head. Okay. So, based upon this we still do not know what is the characteristic velocity. We substituted that into the equation. Divergence of velocity is equal to 0, mass conservation equation. Momentum conservation equation, we have a factor of rho infinity V c square by rho infinity V c square by the characteristic length. Okay. This appears on the left side and it multiplies the pressure if we scale pressure by the inertial scales. The viscous scale is mu infinity V c by L c square, and then there is a scale for the body force, rho infinity beta g into the temperature difference. Okay. That is the scale for the body force, rho infinity beta g into difference in temperature T naught minus T infinity. Okay. Now, we can scale either we can balance either the inertial term with the body force or the viscous term with the body force. Okay. So, the body force has to appear in the dominant balance because that is what is driving the flow. Okay. You can either scale the inertial term with the body force or you could scale the viscous term with the body force. That gives you the value for the characteristic velocity, rho infinity V c square by L c multiplying the inertial term goes as rho infinity beta g into T naught minus T infinity. Okay. Therefore, the velocity goes as square root of L c beta into T naught minus T infinity into g. Okay. Note that beta into delta t is dimensionless, okay, because we know that delta rho is equal to rho beta delta t, which means that beta times delta t is dimensionless. Okay. Therefore, the characteristic velocity goes as the characteristic length times beta into T naught minus T infinity into g. You can verify that it has dimensions of length square. Okay. So, writing the characteristic momentum equation again, rho infinity V c square by L c V star dot grad star V star is equal to minus rho infinity V c square by L c into the divergence, scaled divergence of the pressure plus mu infinity into V c by L c square, the Laplacian of the velocity, okay, plus rho infinity g beta into T naught minus T infinity into the scale temperature difference into the unit vector along the direction of acceleration due to gravity. Okay. And since I have equated rho infinity V c square by L c, right, I can divide throughout by this term. Okay. I can divide throughout by this term, and I will get V star dot grad V star is equal to minus the divergence of the pressure, okay, plus u infinity by rho infinity L c times V c, okay, del star square V plus T star into the acceleration due to gravity. So, that is the momentum conservation equation, and this can be written as this, as you can see, is basically a 1 over Reynolds number based upon the characteristic velocity. Okay. U infinity by rho infinity into root of g beta T naught minus T infinity into L c. Okay, that is a characteristic velocity times L c. Okay. This is 1 over a Reynolds number based upon the characteristic velocity. The way this dimensionless group is traditionally defined is in terms of what is called the Grashof number. Okay. This group is traditionally defined in terms of what is called the Grashof number, is defined as rho infinity square g beta T naught minus T infinity L c cubed divided by mu infinity square. Okay. That is the classical definition for what is called the Grashof number. Okay. Okay. And you can easily see that this is a characteristic Reynolds number square. Okay. This is the square of the inverse of this one. Okay. So, that is the definition of the Grashof number. Okay. And based upon this definition, okay, so I will just write it over here for Grashof number is equal to rho infinity square g beta T naught minus T infinity L c cubed by mu infinity square. Okay. Based upon this, okay, okay, it is a square of a Reynolds number. Therefore, this 1 over Reynolds number here, okay, can be written basically as 1 by Grashof number to the half power. Okay. So, this can basically be written as 1 over Grashof number to the half power. Okay. This is the momentum conservation equation. Okay. This is the momentum conservation equation. So, the Grashof number, as I said, it can also be written as, okay, g beta into T naught minus T infinity L c cubed divided by kinematic viscosity square, okay, divided by kinematic viscosity, because mu by rho is just the kinematic viscosity. Okay. And there is another dimensionless group that is called the Rayleigh number. Okay. There is another dimensionless group that is called the Rayleigh number. The Rayleigh number is written as g beta T naught minus T infinity into L cubed divided by the kinematic viscosity into the thermal diffusivity. Okay. Note that kinematic viscosity is momentum diffusivity and thermal diffusivity is alpha. Okay. So, it can be written in this way as well. Okay. Grashof number is usually large in practical applications. Okay. The Grashof number is usually large in practical applications. It is can be anywhere between 10 power 4 and 10 power 9. Okay. It can be anywhere between 10 power 4 and 10 power 9. Therefore, this coefficient here is typically small in practical applications. Okay. This coefficient is typically small in practical applications. Fine. So, this is the momentum conservation equation. Energy conservation equation, okay, the divergence of V T is equal to the thermal diffusivity del square T. Okay. And using our scalings, on the left side I will have characteristic velocity by the characteristic length, characteristic velocity by characteristic length into T naught minus T infinity into the divergence of V star T star is equal to alpha infinity into T naught minus T infinity divided by L C square del star square T star. Okay. So, that is the energy conservation equation. Okay. Divergence of V times T is equal to alpha del square T. That divergence can be taken in because the divergence of velocity is equal to 0. So, I could as well write this as V dot grad T. Okay. Dot grad T. Okay. I could also write this as V dot grad T, does not matter. Okay. So, therefore, if I divide throughout by this the coefficient of the term on the left, right, I will get del star dot V star T star is equal to alpha infinity, okay, by L C V C, okay, del star square T star. Okay. Now, let us look at what is this parameter. Okay. This parameter alpha infinity by L C V C. Okay. I can write this as alpha infinity by nu infinity kinematic viscosity. Okay. Alpha infinity is the thermal diffusivity by kinematic viscosity times the kinematic viscosity by L C times V C. Times kinematic viscosity divided by L C times V C. Okay. Now, alpha by nu, okay, you know that the Prandtl number, okay, Prandtl number is equal to the kinematic viscosity divided by the thermal diffusivity, which is also K Cp mu by K. Okay. Okay, it can be written as the thermal the momentum diffusivity divided by the thermal diffusivity, or as Cp mu by K. Okay. Therefore, this is equal to 1 over Prandtl number into 1 over Grashof number per half. Grashof number per half is the Reynolds number, as I told you, based upon the characteristic length, characteristic velocity and the kinematic viscosity. So, this can be written as 1 over Prandtl number times 1 over Grashof number to the half power. Okay. So, this is 1 over Prandtl number Grashof number to the half power. Okay. So, to summarize the equations, okay, the divergence of the velocity is equal to 0, mass conservation, V vector dot grad V vector, okay, is equal to minus the gradient of the dynamical pressure plus 1 by Grashof per half del square V plus unit vector along gravity times T star, okay, and V star dot grad T star is equal to 1 over Prandtl number Grashof per half, okay, del star square T star. Okay, so, those are the equations, okay, that we have to solve. Okay. We will not solve the equations, we will just use scaling relations to find out what is the magnitude of the heat flux. Okay. So, we will just use scaling relations in order to find out, determine what is the magnitude of the heat flux. Okay. So, let us restrict our attention to a two-dimensional system. Okay. So, let us restrict our attention to a two-dimensional system. Okay. So, we have this hot object here in a cold fluid, of characteristic length LC, and T naught is the surface, T infinity is the temperature far away. Okay, so let me write T infinity here, is the temperature far away, and we have this, okay, this fluid rising up, okay, due to the buoyancy. Okay, we have fluid rising up due to buoyancy. Okay. If I expand out this region, okay, if I expand out this region, basically what I have is a hot surface. Okay. This region where the fluid is rising, and if I plot the velocity as a function of distance from the surface, okay, I will call the distance from the surface as z, okay, and x is the distance along the surface. Okay. At the surface, the no slip condition, velocity is 0, it increases and then it decreases as you go further away. Okay. At the surface itself, the temperature has to be the velocity has to be 0 due to the no slip condition. Due to buoyancy, the velocity will increase away from the surface, and once again when you go far away, the temperature equalizes to the ambient temperature, and so there is no driving force, and the temperature once again decreases to 0. Okay, so that is the configuration. In this coordinate system, I will write, in this x z coordinate system, I will write the conservation equations. Okay. Partial Vx by partial x, okay, plus partial Vz by partial z is equal to 0. Okay. Vx partial Vx by partial x plus Vz partial Vx by partial z minus partial pressure by partial z plus 1 over Grashof per half into partial square Vx by partial x square plus partial square Vx by partial z square plus the gravitational acceleration in the x direction times t. Okay. That is the x momentum equation. Z momentum equation, Vz partial Vx, no, Vx partial Vz by partial x plus Vz partial Vz by partial z is equal to minus, my apologies here, this should be the streamwise direction and that should be the cross stream direction. Okay, so partial P d by partial z plus 1 by Grashof per half into partial square Vz by partial x square plus partial square Vz by partial z square plus Gz into t. Okay. And finally, the energy conservation equation, Vx partial partial t by partial x plus Vz partial t by partial z is equal to 1 by Prandtl number into Grashof number per half into partial square t by partial x square plus partial square t by partial z square. Okay. These equations we are examining in the limit of high Grashof number. Okay. These equations we are examining in the limit of high Grashof number. Okay. And you can see that in the limit of high Grashof number, if you neglect these terms, okay, if you neglect these terms in the limit of high Grashof number, then first of all there is no viscous term in the momentum equations. Secondly, there is no diffusion in the temperature equations. The temperature equation basically tells you that the temperature is a constant along streamlines. The same problem we had when we were solving high Peclet number problems. Okay. You cannot satisfy the boundary conditions because you are neglecting the highest derivatives in the equation. Okay. In order to find out the transport rates, so there has to be diffusion close to the surface because there is no flow perpendicular to the surface. So, there cannot be convection from the surface to the fluid because of the no penetration condition. Very close to the surface, diffusion has to necessarily act in order to transfer heat from the surface to the flow. Okay. Within a thin boundary layer whose thickness will be determined from the condition that convection and diffusion are comparable within this boundary layer, okay, from the condition that convection and diffusion are comparable within the boundary layer. Okay. So, therefore, I have to postulate a new length scale Z plus is equal to Z by LC times a scaled boundary layer thickness, okay, Z by LC times a scaled boundary layer thickness, and scale the equations using this Z plus rather than Z star, because that is the appropriate length scale over which diffusion takes place. Again, there is a balance between convection and diffusion. Okay. X star is still equal to X by LC, Vx star is equal to Vx by the characteristic velocity. What about the cross stream velocity? The streamwise velocity is the characteristic velocity, the velocity generated due to the buoyancy force. What about the cross stream velocity? Okay. That comes from the conservation equation for mass. Okay. Partial Vx by partial x plus partial Vz by partial z is equal to 0. Scaling Vc by Lc partial Vx star by partial x star. We still do not have a scaling for the velocity in the z direction. So, I will just get 1 over delta Lc partial Vz by partial z plus is equal to 0. Okay. And you can easily see that I have to define Vz star is equal to Vz by delta times Vc, okay, delta star times Vc. Okay, I have to scale Vz by delta star times Vc in order to get a balance between these two, okay, because I can divide throughout by this first term. Okay. If I divide throughout by this first term, I will get here, okay, this will go away and I will get here delta times Vc. Okay. So, therefore, the velocity scale perpendicular to the surface is delta times Vc, which is much smaller than the velocity along the streamwise direction. Okay. The velocity scale perpendicular to the flow is delta times Vc, which is much smaller than the velocity scale in the flow direction. Okay. Mass conservation equation becomes partial Vx star by partial x star. Okay, so, I will just write the mass conservation equation here. Plus partial Vz plus by partial z plus is equal to 0. Okay. I will write this as Vz plus, so as not to confuse by Vz star, which is scaled by the characteristic velocity. Okay. So, that is the scaling for the velocity. Okay. Now, we have to scale the momentum and the energy equations. Okay. We have to scale both the momentum and the energy equations. Okay. So, that scaling I will continue in the next lecture, and we will derive a set of reduced equations, boundary layer equations for the flow close to the surface in the region of thickness delta star times Lc, where convection and diffusion are comparable. I will continue this in the next lecture. I will see you then.